Hello, students, and a very warm welcome to you all. Today, we're going to dive into a really important concept in organic chemistry, and that is the structures of functional groups. So let's get started. I'm sure you must have seen this in the lab. It's a bit of a puzzle. You take some ethanol, you add a nice oxidizing agent, maybe some potassium dichromate, and poof, it reacts, you see that color change. But then you take something that looks very similar, diethyl ether. It also has an oxygen atom, right? You do the exact same thing and nothing happens. Absolutely nothing. So why does this happen? What is going on here? Well, the answer, my dear students, is that just looking at the oxygen atom is not the full picture. The real secret is in the structure of the functional group. It's the arrangement, the entire bonding environment around that oxygen that actually decides the molecule's chemical personality and how it's going to react. So let's properly understand why we are saying structure is everything. See, this is not about memorizing hundreds of different reactions. No, not at all. If you can understand the why behind the structure, then you can actually start to predict reactions. And that, let me tell you, is a superpower to have during your exams. Okay, let's break this down with a very simple idea. I want you to imagine functional groups are like Lego bricks. So the OH group is one special type of brick. Now, if you take this brick and you click it onto a simple saturated carbon, it behaves one way. It becomes an alcohol. But what if you take that very same OH brick and click it onto a benzene ring instead? Suddenly, its whole behavior changes completely. It now acts like a phenol. See, the brick is the same, but where you place it changes everything. All right, now for your exams. Here is a proper formal definition. The functional group structure is the specific bonding, the hybridization, like sp3 or sp2, and the availability of electrons that together determine the chemical properties and reactivity of a compound. The key thing to remember here is that all of these factors, they all work together as a team. And this table here really shows the differences so clearly. Just look. For an alcohol, the oxygen is attached to a saturated sp3 carbon. It's a simple, standard single bond, and this makes it quite reactive. Now let's jump to the phenol. Here, the oxygen is on an aromatic sp2 carbon. And because of the resonance in the benzene ring, this CO bond actually gets some partial double bond character. This makes it much stronger, and look at this, the whole group becomes acidic. And finally, we have the ether. Here, the oxygen is simply a bridge between two carbons. It's stable, it's happy where it is, and it's quite inert, very unreactive. To make this idea even more solid in your mind, let's use a very simple analogy. I want you to think of these functional groups as three different types of bridges. This is going to help you create a very strong and lasting mental picture. So let's map this out. An alcohol structure is like a simple wooden footbridge. It's out in the open, it's very easy to access, and it can be easily damaged by, let's say, heavy traffic, which in our world is a chemical reaction. Now, a phenol is not just any bridge. It's like a big, reinforced castle bridge. It's part of a much larger, stronger structure, which is the benzene ring itself. It's much more stable. And the ether, well, an ether is like a bridge that is completely sandwiched between two big walls or maybe inside a tunnel. It's protected, it's locked in, and it's very, very difficult for anything to get to it and disturb it. Okay, now that we have that bridge analogy, let's build on it. We are going to create three very clear scenes, three pictures in your mind, one for each functional group. Because you see, visualizing the structure is the real key to remembering its properties. First, let's picture the alcohol. Scene number one, you have a central tetrahedral carbon atom, and just attached to it is the OH group. The most important thing to see here is that this OH group is completely exposed. It's out in the open. The lone pairs of electrons on the oxygen are pointing outwards, almost like they're inviting other molecules to come and form hydrogen bonds or react. It's open and it's ready for action. Now for scene two, the phenol. In this picture, the OH group is attached directly to a big glowing benzene ring. Imagine the electrons from that ring are constantly flowing and sharing their stability with the oxygen atom. So the OH group is not just attached, it's integrated. It has become part of the ring's powerful electron system. This reinforcement makes the whole thing stronger, and very importantly, it makes the hydrogen on the oxygen acidic. Why? Because that big ring can easily stabilize the negative charge left behind if that hydrogen decides to leave. And finally, our third scene, the ether. Let's visualize it. You can see the oxygen atom, but notice its position. It's not at the end of the molecule. It's a bridge, perfectly sandwiched right in between two carbon atoms. And what about its lone pairs? Well, they are not pointing outwards like in the alcohol. They are locked inside, tucked away between the carbons. The entire structure looks sealed, protected, and, well, inert. It's not looking for a reaction. Okay, so these mental pictures are great, but you might be thinking, sir, how does this actually help me solve real chemistry problems? That's a very good question. So let's look at a practical application straight from the laboratory. So, in your more advanced organic chemistry, you will learn about the Grignard reaction. This reaction uses a very, very reactive reagent. And the solvent that is almost always used for this reaction is an ether, like diethyl ether. But have you ever wondered why? Why can't we just use a common solvent like alcohol? Let's solve this problem together, step by step. Our goal is to perform a highly sensitive Grignard reaction. The main problem is that our Grignard reagent is so reactive, it will be destroyed by any solvent that can react with it. So let's consider our choices. What if we pick alcohol? Well, remember our mental picture? The open and reactive alcohol with its exposed OH group? It would immediately attack and destroy our valuable Grignard reagent. The reaction would simply fail. But what if we choose ether? Remember its picture? Sealed and inert. It's the perfect non-reactive environment. It will dissolve the reagents without interfering at all, allowing the reaction to happen smoothly. You see? Structure dictates function. This brings us to a very powerful and memorable phrase that I want you to remember. Structure is destiny. In organic chemistry, the type of bonding, whether it's sp3 or sp2, aromatic or not, and the availability of reactive atoms, like hydrogen, completely determine how a molecule is going to behave. So, as we wrap up this discussion, let's just consolidate everything into one final revision note. This is what you must carry with you for your exams. I want you to just remember these 3 simple points. First, the core idea. A group's structure, that means its bonding and its environment, is what determines its chemical personality. Second, hold on to those mental pictures, the open alcohol, the reinforced phenol, and the sealed ether. And third, connect it all to a real example. Ethers are such great inert solvents because of their protected, sealed structure. And I can promise you, if you remember these 3 things, the core idea, the mental picture, and the real-world example, this whole topic of alcohols, phenols, and ethers will feel so much lighter and so much easier. You'll be able to move from just memorizing reactions to actually predicting them. And to leave you with a final thought, based on everything we have discussed today about structure, can you think about why the COC bond angle in an ether is bent? It's around 110 degrees, much like in a water molecule. It's not a straight 180-degree line. Why do you think that is? Think about the hybridization of that central oxygen atom and its lone pairs. We'll explore that next time. Thank you for listening, and keep thinking like a chemist.